say we are in fact live. Hello everyone and welcome into yet another live stream, a special live stream, that is live stream number 1050. And today I have gotten a fair bit of a treat for you. First, let's make sure everything works. So it does appear to be working. That is good. Okay, so today I have a little bit of a treat for you because it is live stream 1050, a special live stream, and as such we'll be doing quantum mechanics. Yes, quantum mechanics. I've got something really neat and damn it, I don't actually know quantum mechanics all that well. I mean, I made a couple of videos, but they were all basic, really basic. I need someone with experience, someone who knows the topic well, someone who it's his specialty, someone who knows it inside out, well, like an excitation in the drunk field, someone like, oh, cheers, Remco. Hi. Remco, fancy seeing you around here. Well, isn't that a coincidence?
I heard you needed an expert on quantum mechanics.
I mean, would you mind giving us a lecture on quantum mechanics, actually?
Of course I wouldn't mind. Where would you propose we start?
Oh, that is a good question. I suppose we could start with kind of a recap, right? I think that's a good place.
There'll be a fair assumption, yes.
Yeah, I think we should start with, we have covered the topic of quantum mechanics in the past already, and I think it is time to refresh on all the topics, all the knowledge that we have laid down last time. So, well, that's a good question then. What would be the first thing for us to mention?
I think it might be reasonable to start with linear algebra.
Linear algebra. Yes, so obviously the bedrock of quantum mechanics, we'll be going over it a lot.
We begin with recalling in what kind of system we are. And usually when we want to describe physics, we will be associated, we will have an associated space, the vectors, or in this case, a Hilbert space.
Right. So
with,
there we go. No, carry on.
With a vector space, or the Hilbert space, we can define our quantum mechanical states. We will write states using the bracket notation, where a state is formally a ket that is a vector that lives in the vector space.
Yes, so state being a vector in the Hilbert space, a vector. We're all familiar with vectors, we know them as numbers in a column, there is some more underlying depth to it, but the point is vectors are described, states are described by vectors specifically, in the Hilbert space. It's just one of the kinds of spaces that you can have vectors in. It is defined by being complex valued and a couple of other topics you will see soon, I suppose, when they become relevant.
Yes, so vectors are the basic, the building blocks of the entire formalism,
yes,
let's say. But we can use these vectors to transform into different vectors. And the relevant mathematical machinery for this is called an operator. An operator is a linear function that takes vectors to vectors. So let's say we have a operator A. It will live in the space of linear functions on the vector space. More specifically, this means that A is some sort of function from the vector space to the vector space.
I suppose should make sense. We start with a vector, we end with a vector. That is just what the matrix would be.
One very important one, a very important, well, linear map more specifically, is the covector, or in this case, the bra.
Right. Bras being a bit of a confusing topic because they are described by the same amount of values, numbers, whatever you would like to call it, as vectors. They are, so vectors are written in columns, whilst bras, maps, are written in rows. And they describe the map that we are applying the vector on. That's the idea there, which in bracket notation, very conveniently actually, in a quite elegant way, it notes down the ket as one kind and bra as the other to signify the column versus row.
Yes, so mathematically we would write this down as a covector, or a bra is a linear function from the Hilbert space to the reals, or I guess we could also make it the complex numbers. Now, in physics, we cannot measure states. We cannot measure operators. The only quantifiable objects are scalars. Fortunately, with the machinery we have right now, we can construct such a scalar. Specifically, the inner product.
Yes. So, well, actually, I suppose that I don't have much to mention. I think
The inner product is, in this case, the operator acting on a state, which this is of course a vector. That's how the operator is defined. But we act upon here with a covector. And covectors take vectors to complex numbers. So this is, of course, a complex number. And therefore, thus, a scalar.
And just to reiterate in this case, just to make it clear, that's because I do believe that most people here are at least somewhat familiar with mathematics. Some of you are really well familiar because I see Leo joined in. But just to make this a little more clear, a little bit easier to grasp for those who are new to this kind of notation, it is mainly, for now, just notation, we'll say, which means this would be just this, the matrix, and then there we go. This is the bra, the operator, and the ket. Once again, there is a bit more nuance to it, unfortunately, but we can just say this is just a notational change with asterisk, don't mind the asterisk.
Exactly. As Meike said, vectors or states are just dimensional objects. The vectors, as you know them in classical mechanics, operators are matrices, and covectors are just, well, row vectors, essentially. That completes or concludes the linear algebra part. Let's recap what we did in the previous streams, where we now tend to look a bit more towards the physics of it all. So, with that, let's quickly recover the Hamiltonian formalism, specifically the harmonic oscillator.
Yes. Also, Theo is mentioning that we might want to size up the font height.
That is doable.
So, noted, Theo, noted. We shall from now on.
Perfect. The Hamiltonian, we obviously remember the Hamiltonian of the harmonic oscillator. This is given by the kinetic energy plus the potential energy, where the potential energy is the square of the position. So it is a quadratic potential term.
Yeah. This is, once again, from last time, harmonic just means the total energy of our system. So obviously we have kinetic plus potential. Kinetic remains the same as always. The potential has this kind of form because we want it to oscillate. And if you actually go through the calculation just a little bit, it genuinely isn't much, then you will find that this pushes your oscillator back and forth. Basically, it inverts like the kinetic in the ways that it oscillates. It's a harmonic oscillator, to be convenient.
Once we have a Hamiltonian, we can solve the system, classically. These solutions are given with the Hamilton equations. If you remember correctly, the Hamilton equations are given by the time derivative of the position. I think it is, I will just explicitly write it down because the dots will be a bit confusing. This is given by the partial derivative of the Hamiltonian with respect to momentum. And the other one was similar. The time derivative of momentum is minus the partial derivative of the Hamiltonian with respect to position.
We have derived it last time, last stream.
Solving these two coupled differential equations gives you the solution of the system. However, last time we also treated quantum mechanics. In quantum mechanics we saw that the Hamiltonian, which in classical mechanics is a function of position and momentum, instead upgrades to a operator. And we notify this by putting a little hat on that. Similarly, the position and the momentum functions become operators. And that was a game changer. Because right now, the solution isn't as trivial anymore. The solution in solving a quantum system now relies on finding the eigenvalues and the eigenvectors of the Hamiltonian. More specifically, we would be looking for an expression of the form like this.
Once again, this is the linear algebra that we have explained last time. Because in this case, we have the Hamiltonian operator. Hamiltonian describing the total energy of our system, but crucially, it has a hat on it. It is an operator. It acts on a state, and what we get on the other side is not an operator. This is a scalar value. So this is our magnificent tool, and this is the scalar value of energy. So an actual useful measure we can interpret and work with.
One solution that we saw last time is we can take the position basis and we calculated how the momentum operator acts on the position basis, which turned out to be like a spatial derivative. And you end up with a differential equation that you need to solve for some certain energy. This is not trivial at all and kind of boring. So what we did instead was we made a definition. We defined two operators. Where we have a constant to make sure everything works of position plus I times momentum over W. And similarly, we have another operator with the same constant, where we now have a minus instead. The first one was called the creation operator. The second one was called the annihilation operator. The reason why is because we could write the Hamiltonian in terms of these two creation and annihilation operator. This turned out to be a very simple expression. First of all, we have h bar times omega, which is of course of type energy. And then we find the product of the creation and annihilation operator plus a constant factor. So now, I am forgetting some hats.
All the hats that are meant to be there but aren't there are left implied. That's obviously, we take that for granted.
Yes, we do not have an infinite storage of hats.
Yeah, our budget is very limited hats-wise, which is why I really appreciate Terta $20 just to say awesome in chat. I tip my hat to you. I would have if I had a hat. Unfortunately, our budget ran out on all the operators.
You don't mind?
That's all where the hat budget went.
So, anyways, solving the system now, the quantum mechanical system, requires finding the eigenvalues for the Hamiltonian and the eigenvectors. But this, since this is a constant term, this implies that we can just find the eigenvectors and eigenvalues of this product of operators. We did that. More specifically, we postulated this kind of eigenvalue function And it worked out. What we found is that the states, the end states, are characterized by integers. And we could use the creation annihilation operators to move between the steps. More specifically, we had, you could say, a ladder of energies. The ladder keeps going. The lowest possible energy, often called the ground state, has energy where this term entirely vanishes, so you're only left with the constant term. And the other energies would have a contribution. More specifically, every higher level has a contribution of h bar omega. However, the important part is that, say you are in the ground state, you could apply a creation operator, a dagger, and you end up in the first excited state. So with the creation operator, you move between the levels. Similarly, for example, if you are in the third excited state, you could apply a annihilation operator, A, and you will find that your system is now in the second excited state. So these two operators, creation annihilation operators, also called the ladder operations, are the tools to move between the energy levels that are, very carefully, discrete now. So I think it suffices to say we have now the introduction for the quantum harmonic oscillator.
There we go. This is what makes it quantum. It is quantized. Right here, just to make this really as clear as it can be, we have the energy, right? The lowest possible energy state, and you can only move between these energy states at a distance that is defined using this creation annihilation operator. Also another thing, which is quite curious, to be honest, I've never noticed it before, the energy is given by h bar omega. So like h bar times frequency.
Over 2. This is
well, no, what I mean dimensions-wise, like h bar times frequency gives energy.
Mm-hmm.
I never.
That is a consequence of this prefactor being here.
Yeah, I never noticed that h bar and omega, like dimensions-wise, gives energy. Oh,
It turns out to be important.
Yeah, it certainly is. We just quickly see if there are any questions.
The ground state energy is in this case called a vacuum energy.
Yes.
I have said this before. This will turn out, the fact that this is non-zero turns out to be very important in later studies. For now, we continue, unless there are any questions.
I do believe there are, in fact, not. Does not appear to be. Oh wait, can I just ask what exactly these operators measure? Depends on the operator. The Hamiltonian gives you the total energy because that's the Hamiltonian. You can have momentum, you can have position. Basic idea is you have operator acting on a state, giving you a corresponding eigenvalue and then the state. So depending on what kind of operator you use, you'll get the corresponding eigenvalue. Energy, you get energy. Momentum, you get momentum. Position, you get position. That kind of idea.
More specifically, it's written like this for energy. We could also indeed consider momentum, in which case you would have the momentum operator acting on some arbitrary state. Let's call it phi. And what we would find is the momentum scalar, the value of the momentum of that state.
Yes. Put care to the fact that this one does not have a hat. That is the measure that we get, basically.
Yes. So the object on the left is an operator, a matrix, if you will. Object on the right is a scalar. It's just a single number. It multiplies the vector, the state. I suppose it's time.
I suppose it's time. It is, I believe, recap-wise, all we have. We did speed through it right now, but do not worry. We have went through it in a lot more depth, especially last live stream with the creation annihilation operators. So if you would like to see the absolutely beautiful derivation, then I would suggest you check that out. Are you running low?
Yeah, nice to you.
Yeah, I can. No, it is strong, isn't it?
It's good stuff.
It is really
I
quite
just really
strong.
like this stuff.
Cheers to that.
This is going to be a fun stream.
It really is.
Our next topic will be time in quantum mechanics. Until now, we have considered specific states, called an alpha, that live in some sort of vector space, the Hilbert space. However, we have never specified the time. We have never talked about evolution through time, temporal dynamics, see how this changes when you hit the time button, unpause button. We will consider that now. More specifically, we are going to say, we're going to define this object at a certain time. So what we're going to say is, we have the system is in some certain state, in this case the alpha, at time t0 in this case. That is going to be the way we write it down. We're doing nothing here other than saying the state that the system is in right now is at this time.
Yes, does that make sense to it? The thing is, the cat described the state of the things we've been working with, but at no point did we specify at what time. And obviously, things, can they change over time? I don't know. Like in our universe, I'm pretty certain time exists.
Let's just carry on with the math. We'll see.
We'll assume it exists for now.
Let's just ask the question you're asking. What does it mean when we say this state, but with a different time? What does this mean? More specifically, is there a way to relate this object, the state at time t, to the state at an initial time t0? Let's think about this for a second. Second has passed. Time does move.
No, good to know, good to know. We're really doing physics today.
Consider this as our Hilbert space. That looks a lot like Germany. Our initial state at time t0 will be somewhere here. Our other state at time t is still a state, which means it's still a vector, which means it's still in the Hilbert space. It must be somewhere in the Hilbert space. It could be the same vector, but it could also be a different vector. We have no clue. So this is where we will find the second state, say, and this is where the initial state is. Now what we do want to know now, how can we go from this one to this one? More specifically, we have a vector. We want to end up with a different vector, entirely undetermined, unrelated to this one. How do we do that?
So we would need some kind of mathematical object here that transforms one vector into another. I wonder what kind of object could we use?
Let me try something. Yeah, this works. We can use a matrix, or in quantum mechanics language, an operator.
Rerunning all hats.
With that in mind, let's write it like this. We want to describe our final state at time t using an operator, let's call it u for time evolution, that takes a state from t0 to t. It needs to have two inputs because it needs to have an initial and a final
Yes,
condition.
there's a difference between evolving from t0 to t and t1 to t, for example. Both these are evolution to the same spot but from a different starting point. Yeah. So, time evolution operator, it evolves states in time. One quick note I will mention, simply because I know some people find it fairly confusing at times, which is that it's noted down normally with the first state you're evolving to, and then the time you're evolving to, and then the time you're evolving from. That's how usually you've foreseen it noted down, which, trust me, can get confusing at times.
Yes, so specifically, state that comes from an initial state by applying an operator to inputs is of course a linear map, an operator, on the Hilbert space, and specifically we call this one the time evolution operator. To be a bit more precise, we are postulating that there exists such an object. We are postulating that the existence of this is well defined. We will look into a bit more properties in a second. But for now, keep in mind, we're just assuming this works, this is valid, and we'll just see where it leads.
Yeah, fingers crossed. I think we should swap places to be completely and be honest with you.
As long as I can have my drink.
Oh, yeah. I was honestly shocked that I was bringing it to the university.
I pull the strings. Let's see some properties of the time evolution operator. First of all, let me ask you guys a question. Am I writing big enough? Am I speaking loud enough? That was the questions.
That is fairly reasonable set of questions. A singular set of two questions, yes.
I will let you answer on their behavior, their thing. And I will continue writing.
Yes, I will just be impatiently waiting. And in the meantime, as you are all answering, of course we have postulated that there exists, once again as a recap, because might as well fit the space. Tis good, I believe, says Ash. Yeah, cheers, Ash.
Thanks.
So far, once again, recap-wise, as we're writing down, so far we postulated that there exists a time evolution operator which would allow us to evolve our states in time, which would be very convenient because that would give us a certain really powerful tool. I won't foreshadow too much. And right now we're wondering what kind of properties that kind of hypothetical operator would have. The operator we postulated. So logically, off the top of your head, you yourself could actually already think about this, what we would like this operator to do. The first one.
Yes, the first property. If we have a state, initial state, and we want to transform it, not at all, which mathematically we write down as the limit where t actually approaches t naught. You can just replace all the t's with t naught. Then think about this. We have a state, there is no time evolution. Of course we stay in the same state. In other words, this operator, time evolution operator, that takes a state from an initial time to the same initial time should be the identity.
Yeah, that's because effectively we have a state alpha at time naught and state alpha at time naught. If we want to take a state at a time to itself, then obviously we can't change it. That's, I feel like it follows pretty simply, hence why the identity meaning that it just doesn't change anything, it just keeps the state the same.
Yes, a bit more mathematical. This one is the identity in the Hilbert space. It doesn't change vectors when you act on with the identity. The second property is not that useful for us, but I will mention it for completeness sake. We could, for example, we know that quantum mechanics, more specifically states in quantum mechanics, have a probability associated to them. Their components describe a probability density, blah, blah, blah. We don't care about all of that, other than what is the probability? If our state represents a particle, what is the probability that the particle is somewhere?
That's a good question. I mean, listen. If we have a particle in our universe, what is the probability that the particle is in our universe? Is basically the question. Write your answers down below in the comment section. We're going to grade them.
The probability I should mention is the inner product of the vector with itself.
Or 1.
It is 1 if we want it to be somewhere.
Yeah.
Now, okay, so at initial time, probability that the particle is somewhere is 1. Easy. What is the probability that the particle is somewhere after we evolve time?
Well, this one should once again be pretty obvious, because if we have our universe with our particle, then after we let it evolve through time, it will not leave our universe. It will still be in our universe. That should be rather simple enough, I would say.
Agreed. There should be an equality sign. Probability that the particle is somewhere at the first point is the same as the probability of the particle being somewhere at the second point, with both 1. For the second equation, we can express in terms of the time evolution operator using the definition, using this. We do need to be a bit careful because technically this is a covector, which means when we want to write this into a graph form, we will get an extra dagger or a joint of the time evolution operator. It is not that important right now, because it has a very clear interpretation. I will come to that in a second. What we see now is that this term, probability that the particle is somewhere, needs to equate this term. More specifically, that means that this needs to be identity, because we already have these. We don't want these to change.
Yes.
So the operator term in the middle needs to be the identity. More specifically, let me write it down first. More specifically, this means that our adjoint of the operator is the inverse. Am I writing off the board space?
You are not. The entire board is actually good.
Perfect. Now, this is what it means for this to be identity. We want something, the inverse times itself is of course the identity. Definition of inverse. What this means is that when we take state, we could interpret it like this. We take state, we evolve it to another state at another time, and we evolve back, then this should give the same state.
Thank you.
So all this probability conservation, what it is saying mathematically is that our time evolution operator is unitary. What it's saying in normal people language, it's that time forward is the same as time backward. It's not that special.
Yeah. Basically, if we have some kind of certain state, if we consider a state in that future, and then if we consider that state pushed into the future and then that state pushed back into the past, then it is basically the same as just not evolving the state at all. It's really the same as just the state evolved to itself, which once again is the identity, because that means no change. We are not getting any questions, but everyone seems to be really interested, so that's actually a really good sign.
Let's get quickly towards the third property then, the most important one. Let's say we start at some initial time, t0, with our state. We evolve over time to a different time, t1. We evolve again from that t1.
Could we write it out really in big lines actually on the board, at least temporarily, I would say?
Yes.
Because this is...
We start at some time t0. Of course, we have the state associated with this is alpha t0. Then we evolve towards another time. The blue is probably up there, yes.
Yes.
We evolve to another state. This is now alpha t at 1. This, of course, is done by a time evolution operator that takes t0 to t1. What we can do is we can just repeat it again. We now have a time t2, a new state, alpha of t2. And this is, of course, given by time evolution operator that takes us from t1 to t2. That is nice, but we can also consider the entire thing in one go. You mind drawing an error for me?
No, yeah, sure. At this point, I thought you would have picked up the message.
No. I like the hope. This immediate evolution is given by a time evolution operator that takes us from T1, T0 to T2 immediately. Now, there is no difference in either going this way or the direct way. More specifically, there should be no difference. It would not make sense if there was a difference.
That should make sense because what this effectively is saying is that waiting 2 seconds is the same as waiting 1 second and then 1 second, which, I mean, yeah, it is. There's just both ways to reach the same point. You can either reach the same point directly or you can reach it in multiple steps.
2, 1. Yeah, same thing. What this implies is that we can decompose the time evolution operator into its product. I will explain this in a second. I'm going to write it down first. There we go. So what this is saying is we can either, once again, evolve directly from T0 to T2, or we need to work from the left because we have multiplied states right here. So the order of operation will be, we first apply this one on our state, and then we apply this one. So we need to start looking at this one. So we first transform from T0 to T1, and then from T1 to T2.
Yeah.
This is called the composition rule.
A very subtle thing which those among you who have actually been more in depth into physics and or mathematics will just take as obvious, but those who haven't will take as shocking, is the fact that we unfortunately need to say goodbye to the notion that connectivity is always a thing and you can just swap things around at will. A times B does not equal B times A anymore, unfortunately. Or very fortunately, it leads to some very interesting things.
That concludes the properties. We have now listed the 3 properties we desire from our time evolution operator. Well, that is, once again, a postulate. We are postulating that there is one. If there is such a one, if we want it to make sense in terms of physical and mathematical rigor or verification, anything, these 3 properties must be holding for the time evolution operator.
Does anyone have any questions at this point? Because so far what we have gone over is the recap of the quantum mechanics, which basically this half of the board sets up the quantum mechanics. This half right here goes into the time evolution in quantum mechanics. Basically, we're adding time to our universe. Just another Tuesday, even though that invents a Tuesday. So, is anyone confused about any of the steps so far?
I have a question.
Yes. Oh, yeah, of course. Absolutely.
Cheers.
And cheers to that. Oh my goodness.
And now we come to the greatness of university. Wait,
As I says, it makes sense.
Is this still visible?
The very top right corner is
Oh,
not.
no,
It cannot see the paper sun. Now it is. Beautiful.
But here there is this.
Tyler just asked, why does U transpose equal to U inverse?
That is not the transpose, that is the adjoint, which technically is the transpose, but we also take every element to be complex conjugated. It's the dagger in mathematics, or in physics, it's the star in mathematics. The reason why we end up with a dagger or an adjoint version is because we are considering the bra of the state, and going from a state to going from a cat to a bra involves taking the adjoint. More specifically, I guess I could just write it down. If you have a state and you take the adjoint of this, then this will obviously, or this will be the covector, the dual vector. So if you actually now consider an operator in front of that, taking the adjoint, not only do you take the cat version or the Brav version, but you also need to change the order, because taking the transpose of a product reverses the order. So you would end up with this. And that's why there is an adjoint over here. Does that answer the question?
I suppose we shall see, because there does appear to be a little bit of a delay. So in the meantime, we can at least start setting up the next part, I believe.
Right. Next topic. Is this visible stream?
It in fact is, yes, I do believe.
It might be a bit dark.
It might be. Ash, will it be visible?
We don't need to.
No, I think it's visible, yeah. It does appear to be visible. So,
We have set up the time evolution operator. We have shown what properties it needs to satisfy. Let's try to find an explicit form of the time evolution operator to see if we actually can write that one down. If this is actually possible, because could be that we just
we have postulated so far.
Yeah. No.
What kind of tool would we use to achieve such a thing?
I think I might have the good setup. So let's consider decomposition again. Composition, I mean. Let's do it over here once again. Let's say we start with the initial state again. We transform to a state at arbitrary time. State here is given by alpha t naught. State here is given by alpha of t. Let's then, because why not, transform a tiny bit more. More specifically, the time right here will be a t plus dt, where dt is just an almost zero number. It's still non-zero, but it's zero enough.
As always, actually a zero enough. I've never heard it described this way, but that is a brilliant description of an infinitesimal. Not quite zero, but zero enough.
The state, of course, at this final point will be alpha at time t plus dt. So it's almost t. We could, once again, by the third property we postulated, consider the immediate evolution. So let's just write down the corresponding time evolution operators. First, let's just do first the big one. We go from time t naught to time t plus dt. And this needs to be equal to the evolution. Oh, let's do the second one first, because we know we have to start with the rightmost one. Evolution from t naught to t, followed by the evolution from t to t plus dt. We have now used the third condition, composition.
This right here is this step, and then the small one is the one afterwards. This is the large one. That's the basic idea.
Cheers. Now, let's have a think. We have said that dt is small. It's really small. It's zero enough. Let's see what properties we have.
Well, if it's zero enough,
This one we used.
Yeah,
Unitary.
not really. I mean,
Backwards time? No, we don't use that. Maybe we should try this one.
yeah, I mean, if it's t and then t plus dt, that's really close. That's just t to t.
Since we are only transforming a tiny bit, so we're a tiny bit close, we're just a tiny bit away from evolution operator of the same input, we must be a tiny bit away from 1. This calls for the regular rule in physics. Let's focus down on this one. So let's ignore the rest. Let us write it down. As argued, this one has to be really close to 1. So let's just say it's 1, but correct it a little bit.
That makes sense.
Classic Taylor expansion. Can I just say?
A physicist's favorite tool.
A Taylor expansion is given by a first order, which in this case is 1. We're Taylor expanding around the identity. The first order correction, it needs to be small. The smallness we can play with is the evolution of time. So it will be of the form dt. However, we're working with an operator, which means we need to have an operator right here. Let me add the hat for this one.
Just noting down omega because there has to be an operator there.
Yes.
We'll figure out what that operator is, I imagine, in a second. We continue on
Yes.
the Taylor expansion.
Omega just looks cool, especially if we put a hat on top of it. The next order should be, of course, the square of the operator, which the square of the operator is just applying it twice. Now, and we of course have the dt squared over the 2 faculty. The 2 faculty is a convention, it just makes stuff easier. And everything else is of higher order. Now, since dt is infinitesimal, that means like it's really close to 0, which means if taking the square is even closer to 0,
Yes.
it means this term will be much, much bigger than this term. Even worse, this term will be just much more 0 than
Each
the
of
other
them,
zeros.
if the first one is basically almost 0, then the second one is even more almost 0. They're all even more collapsing towards the 0, obviously, and as such,
Yeah, so it makes sense to only write the first constant first and second orders.
yeah, that makes.
The omega is called the generator of the time evolution. It's called a generator because this is the only operator we need to describe this time evolution operator. The omega
That means it's the generator.
as I was no.
Wait, what? What do you mean no? I mean, you just have to. Well, no, that won't work.
It's too general.
I mean, just. Is there genuinely like no way to get the omega?
We need to find something for omega.
There is no. Oh yeah, it's Boschnet, isn't it?
Yeah.
There is. Wait, there is genuinely nothing for the omega. Give us a second. Actually, is there really?
Sorry.
Is there really nothing? There's no way. There is nothing for the omega.
Oh, there's omega here. Oh, fuck. No, it's spherical radius.
Give us a second, everyone. The stream will resume shortly.
How do we interpret this omega?
Well, okay. You know what? At this point, we might as well. The jig is up. We'll be honest. Yeah, Ash is in the room with us because just in the background, and Ash has done some mathematics. So Ash, listen. How do you get the omega?
I mean, I literally wrote a paper on it, so.
Well, he did. We have it somewhere. No.
Operator very Taylor constant.
Yes, this is the one. This is yeah. Okay, hold on. Now it's the setup. Yeah.
No.
Table, no. Operator value.
I think that's it.
Oh yeah, operator value Taylor expansion. That is
Yes.
operator value Taylor expansion. Analysis of the time evolution operator. That is.
Yep. Keep going.
That is remarks, no. Oh, last page. Hold on. So it says here, the exact form of the generator of the time evolution operator to my knowledge, cannot be derived from mathematical principles alone.
That is
It cannot be derived from mathematical...
Wait.
Hold on.
Where's my chalk? Emergency. Okay, got the chalk. Not mathematical principles means physical principles.
We're doing physics.
We're doing physics.
This is a physics live stream.
I'm a theoretical physicist.
Yes. Right.
Let's see. Okay, new glasses. Time evolution operator. Let's put the head because you're a physicist.
Yes.
DT. Head.
DT, that is time.
So, how do I say this best? The Taylor expansion, first order is a constant, is the identity.
Yes.
Identity does not have any units. It's crazy how we must
Yeah,
resort to dimensional analysis.
Yeah, it doesn't, it's not obviously.
No units.
We're adding time.
You're right, this is of unit seconds, which means the generator, the omega, needs to be of units 1/2
Frequency.
It's a frequency.
It must be a frequency. Obviously, you can't add meters to seconds. You can't add a constant to a second. You need the units to be the same. So basically, oh wait, but
It works in the later orders as well. If this is 1/2 squared, this is second squared. Matches
yeah,
up.
that's good. Okay. So now all we need is an operator that gives us that is a
Hold on.
frequency.
We're working in quantum mechanics. In quantum mechanics, we have a frequency. We always have an h. If we don't have an h bar, if we don't have an
Wait,
constant,
hold on. Frequency and h bar.
yes.
That. Oh, damn it! That rings a bell. Frequency and H bar.
Okay. Consider particle. It's a photon. How would you describe the energy of this photon?
Energy is h times omega. It's h bar times the frequency. Which means,
Frequency is energy divided by h bar.
so this, since it's an operator, the energy obviously would have to be the operator. It would have to be the Hamiltonian.
So the generator of the time evolution is a constant times the Hamiltonian over h bar. The constant is you can take a constant because we are proposing a time evolution operator, and we are going to also immediately specify the constant. More specifically, we are going to say that the constant equals minus I.
Yeah,
Why are we doing that? Well, because this will immediately imply that our Hamiltonian is emission, which means if we take the adjoint of the Hamiltonian, we will find the Hamiltonian again, which immediately applies energy as the eigenvalues of the Hamiltonian is real, which I think is a fair assumption.
I would say that energy being real does make some intuitive sense.
So,
That's neat.
that's actually made some space for this grandiose discovery. Holy shit, we're smart.
We're honestly. Can you believe that Oppenheimer gave a lecture at the University of Leiden in Dutch?
Ik kan ook een lecture in Dutch geven.
I'm not saying we're better than Oppenheimer. I'm just saying Remco did it, can do it much better with fluent accents.
De tijdsevolutie matrix wordt gegeven door de identity min de complex getal of de generator dat nu de Hamiltonian is. I will just continue in Engels.
Yeah, now that we have proven that Remco is in fact better than Oppenheimer, we can just carry on normally.
What I need to
Right.
So, h bar, let's write the Taylor expansion. Like that, and we consider higher order terms.
Well, now it's a lot cleaner, a lot more understandable, a lot more concrete.
Let's go back to the equation we started with, the decomposition. Let's write more specifically let's see if we can move this away. Let's also immediately take the limit, where dt is going to 0, so now we're actually considering it to be an infinitesimal. It's 0, but actually close enough to 0, even more closer than I said before. What we do find is that we could write it in terms of this, but this we can express as a Taylor function, specifically on this term. We're going to take dt to 0, which means we're only going to care about the linear, or the constant term, and the first order term. More specifically, once again, take the limit on either side. And we have 1 minus I Hamiltonian dt divided by h bar times whatever remains. Perfect. We're going to do one more step. I would like you to set up the step while I look for more chalk. So
That's very
lay down the reserves.
Okay. In our case, I suppose I should maybe go over everything because it has been a bit chaotic with what we've done.
Yes.
We've postulated the time evolution operator, which I hope you are all already familiar with by now. Now, the important part is postulated. We don't know if it exists, we just assumed, we're just trying to throwing things a bit against the wall and trying to see where they lead. And then, obviously, since we have our time evolution operator, a nice way to bring it into existence would be to define it in some kind of way that would actually allow us to use it. And the way we were going to do it was with the Taylor expansion. Except, there's a problem. Mathematics can only get you so far. And this cannot actually continue on mathematics alone. Fortunately, we are here joined by a brilliant physicist, and as such, we got this. We got a Taylor expansion of the term right there of u from t naught to t plus dt. We have it up to this point, from which we get this equation right here.
I don't know it all of them, but I think some credit deserved to the mathematician.
Yeah, I mean, Ash, well, a little bit of credit on writing a whole 10 pages long paper which lists so comically dense and goes so unbelievably in depth into the Taylor expanded operators. Because an important thing to mention is that most of you are probably familiar with the Taylor expansion of functions. And very crucial, right here we are talking about operators. Completely different thing. It requires a lot of legwork to get to, and you can actually read this document yourself on the website. https://makeit.wtf, and then at the top, quantum mechanics, and then over there you will be able to find this exact paper written by Ash, which actually goes in depth into the Taylor expansions, especially when it comes to operator value functions and operators. Because that is genuinely a completely different kind of worms which required a lot of mathematical legwork. But, with that in mind, what have we got here? Well,
I've done a bit. I've got bored. So what I've written down is I have manipulated this equation. More specifically, I have multiplied out the brackets. So we get a u t naught minus u t naught times this entire thing in the reverse order. And what I've done is the single term, the ut naught, I've brought to the other side, right here. And then I have divided both sides by dt.
that's curious.
For no particular reason.
That's a curious equation. I'm actually curious where we will go from here. Does anyone have any ideas on what we should do with this kind of equation? This is what we have. On one side we have a limit as dt tends to 0, and then we have the time evolution operator, difference of dt between where they evolve, divided by dt. Does anyone have an idea where we should go from here, maybe? Well, I suppose we need to do it. Oh, are you out? So you seem so upset.
Yeah, sometimes I'm aware I just speak a lot.
I mean,
it's part of the
to be
job.
fair, it's not that healthy, is it? This I don't think is all that. Oh, we actually run out.
No. Well, are we almost done? Ash, can you get a new bottle?
Oh yeah, that would be nice. I can pick it up for you.
So,
Yeah.
I have an idea how to solve this. What we are seeing here, effectively, if I just may assume as a physicist that functions, or that operators are functions, right, t of t plus dt. We ignore the t zero part. The second term will then be the function of t. That is all divided by dt and taking a limited over. This is, of course, the definition of a derivative of the function. More particularly, the derivative of f with respect to t.
And may I say, it does look devilishly similar to another equation on the board.
When you put them too close, it's like too obvious.
God damn it. The jig is up.
I'm sorry for ruining that bit of yours. However, what we do see is we have the derivative of, the time derivative of the time evolution operator equals minus I over h times h. I am going to throw the minus I over h bar to the other side, which will result in I h bar. And we leave the h over here. And of course we still have.
Yeah. So this is the equation we end up with, and I do believe right away we might as well write it down in a different manner, can we?
Well, this is an operator. What is an operator without something to act upon? Let us resummon epically our states.
States the entire time have been left implied. Operators on their own don't make sense. All of these.
They do, but not enough for us.
No. States the entire time. As I mentioned, everything missing is left implied. You need to be on your toes. We never forget to add things. They are always left implied.
I have resummoned the states, and now I can just use the definition of a time evolution operator, which will give the epically simple.
This evolves it from T0 to T, which means we get the state at T instead of state at T0.
What we have here is the time dynamics of states. More specifically, a state that depends on time. When we take the derivative, which is essentially describing the dynamics, you see how it moves over time,
Changes.
is determined by the Hamiltonian. In other words, it makes sense that the Hamiltonian, it makes sense when you say that the Hamiltonian governs time.
Yes, and I do believe that there is another way to write down this equation that is a bit more.
Yes, I can write it down in words.
Oh, that's good. Well. Because the equation does actually have a name. A name some of you might be familiar with. It is the one, the only, capital S Schrödinger equation.
We have, on the assumption that states evolve in time, with the postulate that there exists some operator with some certain properties, specifically these three properties, derive the Schrödinger equation.
There we go.
Even better, you can do it yourself. You can fill in the steps that we have left implied. Put all the heads everywhere. You can solve your own Schrödinger equation. Now, some of you might be arguing a bit like, this is not the one I have seen before. And you would be right. Because a natural continuation is we don't also know what alpha means. We don't know this is a general state. We don't have usually specifics of states. We don't know how the Hamiltonian acts on this alpha in particular. But we do know how the Hamiltonian acts on position states, usually. So what we can do, mathematically, we project our expression on the position basis. A little bit in equation, this comes down to writing this. We're just multiplying with a bra position, if you wish.
Yes, that's mathematically, as a very loose interpretation, you can think of it, Hamiltonian gives you the total energy, and as we have discussed in the past, it gives it to you based on position and momentum. In quantum mechanics, same difference. So right now we have a state which has the information about our system, and the position graph allows us to get the position information of our system. So if you take something that gives you energy based on position and something that turns a state into that position information, then put them together. Congratulations! You can get out the energy out of a state. That's the loose interpretation of this case.
Yes, and we can make a definition because this is a function technically. If you fix your x and your t, if you fix your position and your time, you get a scalar. So it is a function of x and of t. And we write a shorthand notation for this using a psi subscript alpha x of t.
And yeah, so that is basically that's once again the graph from before. Extracting information, specific information out of the state.
Yes, and this inner product or this function is called the wave function, the ever so famous wave function. Once again, states are vectors in the Hilbert space. The wave function is a function as an inner product. So wave function is never a state, it's an inner product, it's projected. It's are the components of a vector basically, in some particular basis, mathematically.
So there, we have very slowly tuned into it, and we have been very casual about this, but this is actually a really big deal. And that's not only because the Schrodinger's equation is written with a capital S. This is actually a really, really big deal, because you might have noticed that the postulates we have written about our time evolution operator are really general, hence why we have the problem with the omegas. So actually getting the way that, getting the time evolution this way also becomes a really powerful tool. This basically tells us how the states change over time, which is exactly as powerful as it seems. Especially since, keep in mind, we started with states not having time dependence at all. This is, I would say, a massive journey. And if anyone has any questions, say them now.
I'm sorry, I got carried away by my thing. This is the fuel to lecture. So,
I think we shall split places.
yes, we shall. This is indeed the so-called Schrodinger's equation for wave functions, specifically position wave functions. That is good. We can express our states or our components of our states in terms of time evolution, the Hamiltonian just governs everything. However, at the start, we set up a quest to find the time evolution of states, the time evolution operator more specifically. We would like to write down an expression for this time evolution operator. So let's do that. We have somewhere this equation, and let us rewrite it once again.
Can I ask questions in the comments after the stream? Yes, you very much can. That will also be encouraged because we will be answering all the questions on their own separately in the future with a lot more in depth. Also, there will be another resources which might clear up those questions. Foreshadowing, once again. You shall see. That's what will be foreshadowing.
We started or we derived this equation in the Schrodinger's equation. This is an operator from now on pretend it's a function. Once again, also a function. It works better that way.
Operated by a function, of course not.
Yes. Don't look at me like that. What we have here is we have a first order time derivative of an object that we consider a function equals a number. Maybe I should add the string, the Hamiltonian. Add some value times the same object. How is this usually solved?
Well, that's a good question. The derivative of a function in relation to time equals...
Yes, something like that form like this.
So it is a derivative of a function in relation to time equals constant times that function.
I believe it really expressed like this.
I could have a guess.
This does it work?
Exponential? Well, shivery timbers, that does work.
Yeah, it runs. Calculate it quickly. Exponential. So we are looking for a solution of this in terms of an exponential. But now we have run into a problem because, okay, I have to admit, these are not functions, they're operators, which, what is an exponential of an operator?
That does not make much sense.
That would be like an e to the power matrix.
Yeah, no, that's rough. That's rough.
It's time to change that. Let's look at my paper. Let's instead propose a solution called an ansatz. Let's say we write this. First of all, we're going to write our time evolution operator as unity plus minus I h times t minus t naught all over h bar plus same thing of square. Notice that the Hamiltonian is not a function of t minus t naught, it's a product. This is actually t minus t naught times the Hamiltonian. I have made that mistake many, many times. And we also have like higher order terms in, say what, t. I wrote this down inspired by the fact that the Taylor expansion of an exponential has this kind of form. But let's see. Let's just take the time derivative of this object. Time derivative of identity vanishes. It's gone. Perfect. Time derivative of this is linear, which means this entire term, the term t just vanishes. We're only left with the constant. So we get minus IH over h bar. Next term, 1/2 times something with square. That means we have to take the derivative. To get the phone cancels the 1/2. 2 will become a 1, so we end up with a term like this. Perfect. And then we can consider, we obviously have the higher orders, which is now order square. What we can see is we can extract minus I Hamiltonian over h bar. From this term, we will get the identity. From this term, we will get minus I h bar t minus t naught, etc. What we see is this term here equal to this term here. So we can just substitute it. More specifically, what we get is minus I h bar times u t naught. for the dramatic effect, what we have found is this, which is exactly the same as here. Solution works.
Brilliant.
So this is actually correct. And now we're going to make a definition. Because we are going to define this object. We're going to define this object as the exponent. More specifically, it will be the exponent of minus I Hamiltonian So, whenever you see an exponent with an operator in front of it, it's just a shorthand notation for this extensive sum. And sums and products do make sense with operators. It's just a nice way to write it down. Inspired by Taylor's functions. Mostly that.
That's all the best things in life are.
Now, I have not mentioned one thing, which I definitely should have mentioned. This approach only works when Hamiltonian is time independent. Let me write it down mathematically. So the reason why is because when you're taking a derivative of this term, and you have Hamiltonians with that depend on time, you will end up with product terms, which it would ruin it. One way to generalize it is by, I guess we can cover that real quick. There is one specific case where the Hamiltonian can depend on time, where it still works, and that is if the Hamiltonian at one time followed the Hamiltonian at another time. If this commutes, which means we can just change them around, then we can also express the solution like this. Once again, it will be an exponent, which, remember, it's just this long form. But now, it will be minus I h over, minus I over h bar, integral from t naught to t of h that depends on t dt. The nice thing is, the derivation of this is left as an exercise for the listener. It's doable, don't worry about it. For the general case, if you just have time-dependent Hamiltonian, I wish you a lot of good luck. So I suppose we have filled the entire blackboard.
That we sure have.
We have found a expression, at least in the time-independent case, expression for the time evolution operator in terms of the Hamiltonian, just the Hamiltonian.
The really nice thing is that, once again, I know that I am sounding like a broken record here, but it is an operator which we have at the very beginning entirely postulated with basically nothing to go for. But right now, what we have reached right here is a very, very clear and definitive equation for it, you could say. So with this right here, we can not only use the time evolution operator, we can even calculate it if we wish to do so.
Yeah, it's much stronger what we have done. What this expression is saying us that if we have a Hamiltonian of a system, we can calculate the time evolution operator. It's not a postulate anymore. It's just given.
It is something that we can directly just calculate right now.
As long as we have a time Hamiltonian, yes.
It is really, really powerful.
Okay. That I suppose concludes the first part of the stream. We have done it. We have nailed it. Time for an example.
I would say so. And what kind of example do you have in mind, actually?
Oh boy, you wait. The guesses are open. The gambles are also open. I'll go clean the blackboard for a bit.
Put your bets right now. What will be the example we're going to use to showcase the time evolution in quantum mechanics?
I will erase this one as well.
I really like these bits where we do something new, you know, or something completely new with something we haven't done before. Because last time we did the harmonic oscillator. On the stream before that, we also started that stream with the harmonic oscillator. On the stream before that, we did the harmonic oscillator. In the video, we did an additional harmonic oscillator. And I am not quite certain, but I do believe we may or may not have as well, as a brief starter example, have done, I think, a harmonic oscillator? Anyway, I'm getting ahead of myself. What will be the example this time?
Are you betting? Yeah, so the example this time, we'll have to wait a little bit because there's one more thing we need to uncover. So, until now, what we have done is we have taken a state, an arbitrary state, and we have transformed it using the time evolution operator. More specifically, we have used it and we have achieved, we received a state that is defined at some later time. That is the definition of this, that's this one. However, in quantum mechanics, it doesn't matter what states are. We cannot measure states. We cannot extract information. We can extract information out of states, but we can only do so through scalars. So let's just say we have an object, an operator, where we want to know some properties of. Let's just say x. Seems like a nice symbol. It's an operator acting on the Hilbert space, which means it takes vectors from two other vectors. Then an object of interest would be the inner product. I think this one, where we are now calculating some sort of probability, which means the bra and the cat needs to be the same. But the object of interest would be this. We could calculate this, we get the probability of the eigenvalue of this operator being this in this state, blah, blah, blah. It's not very important right now. What is important is that we can express this in terms of the initial state. This is obviously equal to alpha starting at t0, evolved by a time operator, the adjoint because it's a bra. Then this, of course, we still have the x. We have the time evolution again from the cat. And we have our cat itself at the initial time. So let's write this slightly different for no reason at all. Let's forget about the t not dependence in alpha. So we're just going to write this as alpha, as we did in the all the way at the back, somewhere there.
In the center of the board.
I love this stick. Alright, we still end up with the operator, of course, time evolution operator. Now our x, we can just say this was at some given time, let's say no reason whatsoever, t0. And we still have our time evolution operator. And we have the state, which loses the t0 information. It's literally the same. I'm just writing x as x t0, and I'm just writing this in terms of it losing the t0. Now, we might have said at the beginning, the states are evolving. Operator has no time dependence. Wrong. Well, not wrong, technically right, but I am also right. What we can define is the following object. We can define the time dependence of an operator as this thing here. More specifically, I will explicitly write it out. This. What then happens is that this object will be equal to initial state, time-dependent operator, initial state. So, what we see is, on the most left-hand equation, we have a state that depends on time, operator that is static. On the other hand, we can write this in terms of an state that is static, operator that is time-dependent. There is two ways of going on with this.
Swap them around.
We have swapped them around. So we started with time, the states are time-dependent, but it is entirely equivalent to say that states, or that the states are static and the operators are time-dependent. These have a name. More specifically, the entire quantum mechanics, where you consider your states time-dependent, this is called the Schrödinger picture, or the Schrödinger interpretation. I wonder who the guy is. On the other hand, taking the matrix states, or the operators as time-dependent, this is called the Heisenberg interpretation. And if you are aware of Heisenberg, he is the one guy that just made the entire operator matrix formalism of quantum mechanics. So it makes sense that he started here. Whereas Schrödinger basically did whatever we were doing and ended up with the Schrödinger equation. Once again, the key point here is it is important that states time dependence can be written in operator time dependence and reversely. Doesn't matter which one we're choosing. It depends, like, usually you choose one of the two because it will make your equations simpler, or it will make your equations look like they have more sense. But once again, it's equivalent.
Makes sense. That does make sense. The time dependent switching up what is time dependent.
Personally, I am in favor of this one. I like my operators to evolve in time. That's just a preference, and since I'm the one giving the lecture, we will continue with this one. So, example time. I take everyone has placed their bets.
I'm certain everyone has internally put the bets for what their example will be. We started with the quantum harmonic, well, we started the harmonic oscillator, which we have made quantum.
Yes.
Now we have time dependence. That is the thing.
Yeah. So natural step would be, let's look at the time dependence of the free
Free
particle.
particle. I mean, if you want to, look at the time dependence of a quantum free particle. I would do it.
The quantum harmonic oscillator as function of time. Abuse of notation right there. So, where do we start? Yeah, so we had these nice operators, A and A dagger. We would like to make them time dependent. Heisenberg picture. And now it kind of makes sense why I'm preferring the Heisenberg picture, because making the states time dependent, that doesn't really give a lot of information. It gives the same information, but it's like you need to work your way around it. Whereas making this time dependent, just you can use this. You can write it in terms of this, make this time dependent, etc.
So basically, these are our creation annihilation operators from before. and because we apparently are picking Heisenberg over Schrodinger's, because it's a fact that it's better. Remco stayed as a preference, which means a fact. As such, we now have them evolve in time.
I'm going to add one ease of notation. T0 is going to be 0. We just
That does make
pick a
sense.
particular time. Also better. I'm going to make another ease of notation. The operator of t to 0 now. We're going to just write it as t, operator of t. It's just, we're not doing anything, we're just setting or fixing this and just making less writing work. And it's getting higher. So,
Left implied.
left implied indeed. The definition of the time-dependent annihilation operator is this, which I have just wiped away. But if you remember, it was here. I will just write it down. Time dependence of operator is a joint of time evolution operator, operator at an initial time evolution. You do see that with operator you need two time evolution operators, one the joint, one normal, and with state you only need one because you get the other one in the other state.
That makes sense.
This we can continue with this because we have a Hamiltonian and we know how to express time evolution operator in terms of Hamiltonian. This one, this specifically. So let's write it explicitly from the top of my head, of course. I h over h bar t just a0 and exponent I h minus I t over h bar. Perfect. We have our Hamiltonian. It's all the way up there. So just fill it in. But actually, we don't use this one. We're going to use this one, of course, because we're working with case and annihilation operators.
There's no point for us to this time start with the classical, we might as well start with quantum.
Exactly.
We're time evolving anyway, so we'll do fancy things.
H bar is going to drop out because we have an H bar here, which means we are left with the exponent. I'm going to write this in e power now of I. What do we have? Omega t of a dagger t a plus the constant term, then a 0. Same thing, but now with the minus sign.
The exponent might be a bit small. But it doesn't matter, that can be.
I'll try to write bigger.
Yes.
Locally. Perfect. Now, problem is, this guy, when acting up with this guy, remember this guy is a large exponential. It's like a summation of all the Taylor expansions orders. That means this will have to interact with this. We would like to get this thing to the other side. Because if we do that, then this can cancel this. Because there is a plus sign here, minus sign here. If we have something of the form E minus A, EA, this is of course the volume. With the constant term, we already see it vanishes because this commutes with just the constant term. So the constant term gets over to here, then we get plus and the minus, vanishes. So I'll rewrite it once more, but bigger. Where we now just leave the constant term out. And then it's our job now to see how this one exchanges with this one. Wanna solve it? I think you can. let's just say it's a lot of work. Let's also say it's definitely not trivial. And let's also say exercise for the viewer. This is equal to a times e to the pi I w t, or minus I w t, I believe. Yes. And this is, of course, evaluated at 0.
So, once again, a really neat thing, which is we start with something, well, in this case, we start with a time-dependent annihilation operator, correct? Geez,
Yes.
that's always confusing. Time-dependent annihilation operator. We didn't know what the time-dependent annihilation operator was. We knew what the annihilation operator was on its own. But we have arrived in the end with this, which gives us a way to actually calculate the time-dependent annihilation operator. Exactly.
Correct. We can do the same thing for the creation operator. We will find the same expression. You just swap some plus or minus signs around, and the minus sign that's in the exponential becomes a plus sign.
Which does again make sense if you look at the annihilation creation operators higher up. It all should hopefully make sense. If it doesn't, speak up now or stay silent forever.
Regardless, we now have two differential equations of operators that we pretend to be functions. We have this one, which shouldn't be too hard to solve. This is
When you're pausing like that after saying shouldn't be too hard to solve, you're really undercutting your argument.
They don't even need solving, they're already solved. That was being trivial. Let's instead look at something else. Let me actually what we can do is we can just look at the Hamiltonian. Well, as a function of time for the harmonic oscillator. More specifically, this is our dagger. I'm going to drop all the time dependencies of the time evolution operator. It will be like this. Make sense? This is definition. We fill in the Hamiltonian, which is h bar. So
I just don't think there's something worth looking up on. Basically, it says that the well, the Hamiltonian with time evolution is just time-evolved Hamiltonian. That's basically it.
yes, that's exactly what it is in the Heisenberg picture.
Yeah.
Now we can just fill in the Hamiltonian, but these are evaluated at 0. Now what we can do is something clever. Finally, at long last, we can use the second property, unitarity. So, first of all, let me get the constants in front. What this means is that since this is 1, we can just insert it anywhere. It's 1 anyways. It's like multiplying by 1. We can do that wherever we want. We're going to do that in between the creation and annihilation operator, but in reverse order. So more specifically, we will have this. There we go. Now, this is something we recognize, or you should recognize. This is the time-evolved creation operator, A of t, a dagger of t. Similarly, this one plus this, same thing for the annihilation operator. And the constant term has u dagger times u, which is 1, so we only get the constant term, so we still have the half over here. Now we can just fill in that we have expressions for the time evolution of the equation and annihilation operator. Let's just work it out. What was A dagger again? It was e to the power I omega t. And A was same thing except a minus sign. And of course we've got the half, do not forget. And now we see something funny. Would you like to elaborate?
I only worry that the text might be a bit small to see the funniness, but I do believe it might not be, in which case we can see the two exponentials, one with a minus, the other one without, so the same exact thing.
The time evolution of the Hamiltonian gives us this result. But this result is the Hamiltonian without time evolution.
So time evolved Hamiltonian is just the Hamiltonian.
It makes sense because we assume that the Hamiltonian is time independent. It is time independent. Checks out. But it also confirms that energy is conserved. Because energy eigenstates do not depend on time. Because the Hamiltonian doesn't depend on time.
So there we go. Despite introducing time evolution in this framework, the energy still stays conserved. So far, everything works. That's really nice.
Should we do one confirmation?
I suppose we shall.
Because there is a reason I have addressed or I've written down the Hamilton equations. And we can just very easily check it from this equation. We can just check if our entire framework with the time evolution operator works. So let's get to that, I suppose. Which means time evolution is not necessary anymore.
Yes, so in this case, we are bringing the Hamiltonian of the quantum harmonic oscillator, I do believe.
Yes.
We're taking the equation for the Hamiltonian of the time we're taking the equation of the Hamiltonian of the quantum harmonic oscillator. And since we've just shown evolved Hamiltonian is the same as non-evolved one, we might as well use it in the time-evolved framework, which means that right now this will be quantum harmonic oscillator, time-evolved. My goodness, that is a mouthful, but I think you understand the idea. We're basically slowly but surely complicating the harmonic oscillator more and more, and right now we have time evolution. So, where shall we begin?
We just start with the Hamilton equations.
Makes sense.
We have the derivative of position with respect to time is of course given partial derivative of the Hamiltonian with respect to p, which is p over n. Factor 2 cancels out the factor 2 here. Similarly, the derivative of the momentum is given by minus partial derivative of the Hamiltonian with respect to x, which, of course, can be readily evaluated. The m stays, the factor 2 drops this factor 2, so we get m omega squared x. Very nice. Now, why did we do this? Good question. I have the answer. Consider the creation operator, which was the constant that I keep forgetting. I remember it. This is the annihilation operator. Now, we can take the time derivative of this, which, since everything else is constants, this results in taking time derivative of this, time derivative of momentum. We have just calculated these, which means we get the same constant back. dx over dt is Pm. And we have the plus I over m omega with the time derivative of momentum, which is the minus mw squared x. So this becomes a minus. M and w cancel. You get a I omega, and of course still our x. Now, how to continue? Well, we can extract a minus I omega, because it's in front of here, and we don't want it in front of the x, with foresight. We still get the same constant, obviously. I'm writing chalk like it's whiskey. We extract a minus I omega, which means we are left over with an x. And for the other term, we extract some 1 minus omega, which means we're left over with an I p over omega m. You want to review or should I?
I think at this point, you might have the honors.
This expression is a familiar one. We started with it all the way over here. More specifically, what we get is the time derivative of the annulation operator is minus I omega. Annulation operator.
Now, isn't that curious? We could. Yeah.
We can solve this.
Yeah, we could put the derivative closer together. I was about to say, just to paint the picture a bit more. Because it's a bit of a deja vu. We have seen this kind of equation already on this same spot on the board, if I'm not mistaken.
I may have wiped it. But yes, it was there.
I don't think we need to give it all its spells. I mean, exponential.
The natural implication of this creation operator, or annulation operator as a function of time, equals a constant, which is the annulation operator evaluated at 0, of the exponential minus I omega t. And we can do the exact same thing for the creation operator, in which case there would be a minus sign here, which would result in a plus sign here, which would result in a minus sign here, which would result in the expression time derivative of a dagger is now a plus sign. So we don't even have to write it down. And we still have a dagger. So we see a dagger is function of t equals a dagger evaluated at 0 exponential I omega t. Which you look about. I think those are exactly the same we have here.
Actually, that proves.
What have we done? We have just verified our theory in 2 ways.
Which means that you can actually evolve in time quantum systems. Very, very, very convenient, I would say.
Yes. It would be boring if it was everything static.
We have to go somewhere from here.
No, we have covered everything. I think let's just wrap it up to make a conclusion.
I do believe so. First of all, questions, in case anyone would have them. Does anyone have any questions? Because let's be honest, this was quite a fair bit lot. The last two are me saying deja vu, Adrian saying deja vu, and then just like immediately saying you deserve a better audience. Do I have a corny bar for you, Adrian? But thank you for your potato watching movies.
Adrian should be taking care of the potatoes.
Yeah, they're still boiling, by the way. We're hoping that you have taken care of them. How were the potatoes yesterday? They were actually delicious. The amount of garlic was inhuman. Will this be saved as a VOD? I just joined. It will not be saved as a VOD, it will also be edited into its own videos, plural. One of them will be just an edit of the live stream, everything that's happening except a tad bit cleaner, more concise. And another one will be dedicated videos to the topics, which will have dedicated animations. Still, like those videos will probably put it in perspective, but right now I would just like to take the opportunity, because in those videos he won't be able to ask the man himself about anything on the board right now. But I do believe that there appear to be no questions. I suppose we can go to the summary.
I will provide a summary then. We started with linear algebra, defining the stage. We continued with a recap of quantum harmonic oscillator, the physics playground. We then postulated, what if there is time evolution? How do we describe that? And we did so with a time evolution operator. We extracted the necessary or needed conditions for that. And we then proceeded to use these properties in a very smart way to derive a defining equation, the Schrödinger equation.
We derived the Schrödinger's equation using the Taylor expansion on it, but very crucially, and this is a step that genuinely I think is quite fascinating, the fact that you cannot derive it with maths alone. So
according to this paper one here.
According to this paper, it cannot be, yes. So this is a curious fact that I just feel like it bears accenting that this is honest physics. At that point, it's not just us deriving equations. You cannot, in fact, get from that to the Schrödinger's equation on just mathematics and following up on equations alone. At that point, we had to basically figure out that the generator would be the Hamiltonian.
Yes.
And based on that, we built the Schrödinger's equation, which gives us the change of a state. It gives us what it's equal to. It gives us its equality to the Hamiltonian itself, which means that the change of the state in relation to time is based on the Hamiltonian, which we then later on carried on, Renko carried on with, in order to write here, it has been wiped, but we went on to actually get the time evolution operator. And in this case, once again, we started with it as a postulate, but then we ended up with the actual equality that we could use from this time evolution operator. And then we were able to use those facts to, first of all, confirm that energy stays conserved. And whilst I do realize that to many watching this must be a shock that energy stays conserved.
I mean, it's even worse, because I assumed energy was conserved, and then I proved energy was conserved.
Yeah, honestly, it's honestly quite something. But it doesn't matter, because the point is, we have reached this, in order to put it into the most concise kind of way I can, we have reached the point where we can already use all of the tools we had available in quantum mechanics with time evolution. And since in quantum mechanics we really have powerful tools for doing whatever basically we want, this basically means that right now in our universe we can open our eyes to the fact that there is in fact time. And yes, we have checked on this live stream twice. Had to be sure.
Still works.
3, we're good so far.
Now,
we'll keep checking it, don't worry.
Yes. So we showed how the framework worked, and then we showed that the framework holds. It's valid. We can use it, we can calculate whatever we want in terms of time dependent with it. Very convenient. This is the end of everything that had to be covered. But let me just give you a brief preview in where we are going to take this.
Oh, absolutely.
If I may. So
first let's start with a brief background info. The entirety of general relativity. No, keep going.
Yeah, so a state is a vector in the Hilbert space, which is of course an object that transforms away from it. Where are we going to take this? Well, we have just seen time dependence of operators. More specifically, time dependence of the equation annihilation operators. There is one more thing we want to add, which is space dependence as well. because they could also depend on space. And once we have done that, we can use these creation and annihilation operators. So we also have this one. We'll just write it in a slightly nicer way. Don't get it if you don't understand that notation. With these two space-time dependent creation and annihilation operators, we can create particles as we like. We can create and remove particles. We can just say like, hey, we want an electron there. We apply a creation operator on that specific time, at that specific location. We have particles there.
Yes.
I wish it was so easy. We need a couple things. First of all, we have a position operator. We do not have a time operator. That is a problem. Second of all, what are particles? Important question. What are particles? I suppose we'll find out next time what particles are.
What are particles?
What are we creating? Excitations? What? Particles?
Excitation, but excitation is what? It's like,
I mean, I suppose excitation in the field is a particle, blah blah blah. So define particle.
but what do you mean? Like it will be a theory of like quantum fields? That sounds mental. Don't even. That's no. That sounds wild. That doesn't. That doesn't sound like.
I think we should stick to definite object circles with some certain values. For example, energy. Example, angular momentum. Example, momentum. Example, this object. We'll leave that for the next time. For now, this was it.
And the next time there will be, I hope you all enjoyed it so far. I really hope you all enjoyed it so far. I do have to say, and I will say it right now, that the reactions appear to be really positive. Emmy at least said that, and you will be rewatching it too, because learned a lot, didn't understand everything on the first try, which is understandable because there is a lot of notation. Also, mathematicians and physicists have this weird interaction between them, where they keep redefining their own things simply because there always has to be a different object in mathematics and a different object in physics, and despite being the same, dual vectors, covectors, different notation for linear algebra, because everything would be too easy otherwise. So the new notation, completely understandable. I will, however, say, Emmy, that there will be a lot more resources to learn from. There is, and there will be. I will get to that in a second. But for now, I guess make it the same thing for the next stream. Obviously, we can't solve all of physics in a single stream. I mean, yeah, Remco could. It's just, we want the watch time. That's the only reason.
I can solve the entirety of TR for you if you'd like.
No. We need to leave it for the next.
It's one equation. Easy.
What is a tensor, actually? I've been wondering that for a while.
So a tensor,
Yeah.
just like a vector, is an object that transforms like a tensor.
That makes sense.
Should I write it down, or?
I feel like we should write it down just at the end what the tensor is. It was awesome. Please keep doing this. Well, about that. Well, if you're not writing it down, I suppose I shall end the stream, because in this case, I want to keep doing this. I do have something to say, which is that we have done those kinds of live streams with Remco in the past. We've done 2 of them, if I am not mistaken, and they were pretty neat. However, as you can definitely realize by looking at this one is different. It is a bit more elaborate, it is a bit more higher production, I would say, and it took a lot more effort to finish. And that's because this isn't just a live stream, there is much more. On the website, https://makeit.wtf. I will write it in chat right now, or to be more exact, I will go to the place that I would like you all to go, which is /quantum checkpoint. Over there, that links all of the current resources associated with this stream. That's because Ash and Remco have actually done a lot more legwork for this than a single live stream can show. There are currently, if I count correctly, 5 different papers available on different topics. 2 of them, for now, to be fair, 2 of them are of the same, similar topic, they're just broken down differently. That is the Taylor expansions of operators, that's by Ash. There is the linear algebra, the quantum harmonic oscillator, the time evolution operator, and a lighter version of the time evolution operator, which honestly I think both deserve a read because they are phenomenal. I have read through them myself. There are also 3 different videos which we scheduled to go after the stream, but to be completely honest, I think the stream just ended up being a bit shorter than it actually was. So I will make them public in a second. I don't want you to go there. That's because we have started a charity, a science communication charity, genuine charity. And this was the first big event of that charity. There will be more videos coming, there might be more papers coming, and there will definitely be updates to the existing papers. There will be more resources of different kinds. There will be quizzes, for example. Caper has already implemented them, we just haven't had the time to finish them up, and there will be so much more on this topic alone.
Caper mentioned?
Caper mentioned, Caper-san in the corner. So I would just like to end this live stream by saying, first of all, hope you enjoyed. I would really like your feedback. And second of all, an extremely warm thanks to Remco, Ash, and Caper, because I really cannot put into words the amount of work they have done. Yesterday, we came back home, if I'm not mistaken, at 7 p.m.
Yes.
And we just started working. We ended up working till 3 in the morning. It was a lot. And then when we woke up today, we started work, and we barely finished it for the stream. It took months of effort, but here it is, and there will be so much more. And I suppose, for now, would you like to say something as a goodbye, in the forms of goodbye?
Well, I guess we should also have some gratitude towards you for allowing this platform of
And
science.
for now!
No, wait. One more thing.
Yep.
Teaser for next time?
Oh, absolutely. There's only one reasonable format for
There we go.
Plus equals and a half. Plus, hold on, plus equals and a half.
Plus minus somehow.
Plus minus half. Yeah, plus minus half. I've seen that before. There is, actually, there is, there's this thing. There is this thing with
Let me
electrons.
demonstrate it.
No, hold on, there's this thing with electrons. There is this thing. I remember, oh, who told me about this? There was, I think,